Oh, and I guess before I kind of forget to, I didn't see any questions in the doc, but did anyone have any questions and specifically, I guess for section 17, since we're going to go into it, that's just like burning in your mind that you just really want to ask right now? No? Okay, that's fine. And of course, as questions come up, we can definitely go over some. So today we'll go over section 17, it's a little out of order, which should be Bayesian statistics. We'll see how long this goes. This might actually not take the whole hour, but who knows? Maybe you guys get really into it or something like that. Or it just take a long time, which I always do. So let me go ahead and start sharing my screen. And oops, Zoom changed up things. Sorry, I'm just trying to look for the screen. There we go. And then Zoom still moves your windows. Okay, so this is actually in the repo. So I'm just going to show you guys where to find it in the resources, right? Is that it's a little bit, I kind of move things around to make it a little bit easier by subject versus like mod 1, section whatever. So this is mod 2, section 17. And I just put it under probability and statistics, and then Bayesian classification. So Bayesian statistics, Bayesian classification. So we'll actually talk about this in mod 3, naive Bayes classification, which uses Bayes theorem. But we're specifically going to look at Bayes theorem, this notebook here. So that's where you can see this guy right here. Okay. So, all right. So Bayes theorem, Bayesian statistics, right? So first of all, Thomas Bayes, literally the badass of probability. Like that's kind of the feeling you'll hear from people who talk about Thomas Bayes. So quick thing about him, basically, again, like I literally search for like, like Bayes, and like this t-shirt, just like, it's amazing. I am not sponsoring this t-shirt or anything like that, but you can buy it from this website. I was like, oh, pretty cool. But basically it's like, so why do people care about Thomas Bayes and everything? Well, Thomas Bayes was a mathematician. I'm gonna get the year wrong. So back in the day, like at some point. And kind of fun thing is that we talk about Bayes theorem. Thomas Bayes never actually wrote down Bayes theorem down on paper. He actually, like in his notes and stuff like this, kind of interesting story, when he passed away, his family talked to another of his friends who's very, like a mathematician, was familiar with the works. Like, can you look through his notes to see if there was anything worth, publishing, essentially? And going through it, they found like this idea of Bayes theorem, and Bayes basically thought it was so obvious that like he didn't need to write it down. And so the funny thing is that Thomas Bayes didn't actually write Bayes theorem down, but the concept of Bayes theorem actually came from him. So it's kind of an interesting standpoint. And there's a whole bunch of ways that you can apply Bayes theorem and like what this means. So there's this idea of Bayesians. So Bayesian statistics, right, and Bayesians are kind of people who follow along like with the idea of what Bayes was kind of coming up with. And so is anyone here a Star Wars fan by chance? Like, I think most people, I think now at least people know of Star Wars, so it's like it's not like ridiculous. Like it's like oh, who's this C-3PO? You guys all know C-3PO. But there's this great article which I'll link to you guys right now in the Zoom chat. But this is a great article where someone takes the idea of Bayesian statistics and applies it to Han Solo in a scene specifically. I think it was the first movie. When I say the first movie, I mean like Star Wars, like episode 4, you know what I'm talking about. So he actually talks about this little dialogue between C-3PO, the robot, right? It says like, sir, the possibility of successfully navigating an asteroid field is approximately 3,720 to 1. And then Han's like, never tell me the odds, right? So like the idea here is like, hey, like C-3PO, really smart robot, knows a bunch of stuff. He's like, hey, bro, like this is not going to work. Like this is very dangerous. We shouldn't do this. And Han's like, no, I'm good. And it's a great read. I think it's a really great, interesting story. And basically you can use Bayesian statistics to kind of figure out, like, well, okay, like obviously they don't die. Like otherwise the story kind of ends there. Like, oh, well, that's not really fun. And basically they kind of break down, it's like, well, what is the real probability of Han Solo actually being able to navigate this asteroid field? And it's kind of cool. They kind of break it down to the idea of something called a prior versus your posterior and the rate of success. And basically trying to figure out like well, what's C-3PO thinking? Like what's based on his data, his database that lists all the different pilots that have ever navigated through an asteroid field, how many actually got through and stuff like that. And then we also use, it's kind of cool is that there's this part that C-3PO is not familiar with, is that Han Solo is a really good pilot. Like he's really good at what he's doing, but it's still dangerous. So it's like good pilot, but dangerous situation. Like how else is he gonna do? Now, of course, we can go all meta and be like, well, we know it's a movie, so he has to go through. But it's like, but what's the danger we should be feeling as the audience, even knowing that Han Solo is a very good pilot? And so the idea there is basically you can combine these two parts of saying, well, how good is Han Solo? And how dangerous is this asteroid field? And it's kind of cool to kind of go through this part. So after we talk about Bayesian statistics, Bayes' theorem, basically ends up being about like a 75% chance survival. Of course, based on this person's like, numbers of like what they assign of how, good pilot Han Solo is. And he's like 75% chance survival. Oh, that's not bad. It's actually like, it's enough to keep you on your edge on like during a movie. Like, they're going to be fine, but you're like, oh, maybe not. So I thought it was a really interesting one, but it's a great like kind of read through here. So I just linked that article. So kind of like, okay, like cool, Star Wars, kind of fun, stuff like that. The main thing you should take from that like article, if you read it through, is basically the Bayesian interpretation of a probability. It's not that probability is like, oh, when we say a probability, it's based on some prior knowledge or belief. So we actually call this the prior, but you'll hear people say prior knowledge or a belief. And what we do, we update this prior, update this belief based on new information and new evidence that we have, which is kind of different from like when you think of probability. Like I think in most people's head, you think of probability is like, oh, this is what probability, like this is the probability of this thing. It's not going to change, right? There's no reason to update. But Bayesian statistics basically says, oh, we start off with a prior and we update it based on evidence. And that gives us a new probability. So it's kind of an interesting take on this. Some other non-Star Wars examples is like, for example, like flipping a coin, which like statistics and probability, I'm so sorry, but like flipping coins and like drawing cards are like the cornerstone of all statistics. Like that's kind of like just a given thing. But one of the examples, like every time I flip the coin, it lands on heads. So what's the next time I flip it? Will it land on heads again, right? So you can think about this, is that if you had a prior belief that, coins are fair, is that 50% of heads, 50% of the time will land on tails, you would expect, like, well, if I flip it heads, it's probably going to be tails, maybe it can be heads, and all that stuff. But if I kept flipping this coin and I kept getting heads, 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 my prior belief of that it being a fair coin is getting less and less likely. It seems more likely that there's at least some bias towards heads, right? It's not impossible to be 50-50, but there's just seems to be more of a chance. It seems more possible that maybe this coin's been tampered with in some way that's not going to land 50% of the time heads and tails and stuff like this. So it's kind of a cool thing, is that we can actually take this information like and update like our beliefs, our probability and stuff like this. So the opposite of this is frequentists. So frequentists in this case are kind of like in the opposite direction of like how you interpret probability. So their interpretation of probability is the limit of frequency after many, many trials. So basically the only way you know the probability is to basically repeat this many, many, many times and then see what the overall probability is. Where Bayesians basically assign a probability to a hypothesis and see how well, and they can update that probability so that you can treat like probabilities like, oh, we think that there is a 50, like the coin's probability is 50% to land on heads. And that is our hypothesis. And we can update that hypothesis with new probabilities, where a frequentist really would say we need to flip it many times in order for us to really tell, is it going to be heads or tails with what percentage of the time? So it's a subtle difference, but it's really powerful. And that's where Bayesian statistics is like really useful, because we can actually start off with saying, hey, based on some evidence or some other idea of what we think it is, we can start off there as a starting off point. And as we gain more evidence, we can either confirm or adjust, our prior belief. Okay. Everyone understanding, more or less kind of, good, cool. So like sometimes I'll say like, like sometimes it makes a lot of sense to be like a Bayesian like thinking. It's like you can think of it like, okay, like we're updating this belief, we're updating this probability. Where other times frequentists, maybe it makes more sense to be like, oh, we're really considering the probability over time. In general though, I would say is that Bayesian statistics allows us a lot more power, where frequentists we basically have to like test it out and like we think of it as a full like truth of the universe. So like, oh, this coin definitely has some probability and stuff like this. There's some interesting stuff. You can definitely read more into this and stuff, and implications of like what is a Bayesian, like thinking versus like frequentist thinking. Okay, so cool. So I talked about this whole time like, oh, Bayesian statistics, but I haven't talked about like the real, like golden thing is the Bayes theorem. So like I said, Bayes never published or wrote down the theorem. And I just think that's so fun. It's just like, oh, he thought it was so obvious that he didn't even have to write this down. Like, it's like, duh. And his friend, Richard Price, as I was mentioning, basically he's the one who went through his papers and stuff like this. And basically he went to go see if there was anything worth writing. I can't remember off the top of my head if Richard Price was actually the one who wrote down the formula. It might not have been him. It might have been actually someone else. But again, it's not called Price's theorem. It's called Bayes' theorem. So whoever wrote it down, I don't know. Anyway, you can look it up for sure. So some quick things of like, like how Bayes thought of this. So Thomas Bayes basically thought of this idea. It's like you can update your belief by doing more evidence. So there's this scenario that he came up with. Is like he had a table behind him. So you can imagine me sitting down and then behind me is a table, right? And I take a ball, right, like a hacky sack or something, and I toss it behind me. That's gonna land and like hit the table. And like you can imagine a hacky sack so that way it doesn't move, right? So I throw the ball and it hits the table somewhere. And then when I say, okay, I'm gonna take another ball and I'm gonna throw the ball behind me. And the idea is if I throw it behind me, it's random. Like I don't have like a good like, aim or whatever. It can land anywhere on that table. And it lands somewhere. And then I have an assistant, who can see all the like the two balls like on the table and stuff like that, and says, where does the first ball land in relationship to that second ball? And so if I kind of imagine this, if I drew this out real quick, I think it kind of helps a little visually, is that imagine I'm sitting right here. This is me. And then I'll just draw the very first ball in like red. And I have like the first ball lands like right here. Okay. And then I throw the second ball, I'll just write these in blue, like land right here. Okay. And the assistant says, oh, you landed, let's say this is right, this is left, just to make it really clear. And this is like above, this is like up, and this is like down. And so I throw the second ball in blue here, and the assistant says, oh, you were to the right, and I'm like basically on like not up or down, like you're just basically off to the right. So in my head, I can think like, okay, like, well, if I threw this ball randomly, it couldn't land anywhere in here, but the first ball landed off to the left, right, of my second ball, right? Which means it's probably on the left side of this, table. Does that make sense? Like the chances of me having over here. And so it's like, okay, well, I can probably guess, like in my mind, I'm drawing this little like lines like, oh, it's probably over the left over here. So I could kind of shade that in or something like that. So like, okay, like before I didn't know where the ball hit, but I can say, oh, it's probably on this side of the table. And then take another ball and throw another ball again, randomly, right? In this case, like, I throw the ball, maybe it lands over like here, right? And then the assistant says like, oh yeah, it landed, you landed to the right and down. And it's like, oh, okay, like, then it's like, okay, like, well, the first ball was, probably meant that they were off to the left, right? And it's like, but the second ball is also to the left. So like that kind of confirms like, oh yeah, it's probably on the left side of the table. It might even be further left, maybe that's not quite true. Like maybe I put it like right here, like halfway, right? It's like, but it's on the second, kind of on the higher part. So it's like, okay, well, then I draw this line up here. It's like, okay, like maybe the ball is most likely right here. And so I keep throwing the balls and stuff like this. And sometimes, I might land, over here, which might really throw me off. Like, whoa, like, like I thought I was way off. I thought the first ball was way off in the corner, but as I do it more and more, I'm going to have more times where I'm going to be closer if I do it randomly, right? I'm going to have more times where it's off to this bottom right corner, which probably means that my ball here is probably closer to the top corner. And you can actually kind of like imagine updating where you think this ball is over time. So what's kind of cool is that, again, like Bayes was like, this is obvious, like, duh, like we can totally do this, right? And so he didn't even bother writing down the formula. But you can actually do this and say, okay, we can actually write a mathematical formula that represents this kind of thing. And that's where we get Bayes theorems from. Okay. Ever kind of imagine this scenario, like this example and stuff like that? Cool. I linked right here, there's a video. I'll share it to you guys too right now. There's this video too from, I actually don't know if it's number 5. I think it's stand-up maths. But they actually do this experiment in the house that Thomas Bayes lived in. So, you know, just to add a little extra flair to it. But they actually do this experiment and stuff. You can actually see how this works. So if you're kind of curious, you can watch that video too. All right, so some math, right? So we got to actually see this Bayes theorem that Bayes never actually, see, you guys are so blessed. You guys get to see Bayes theorem, and Bayes didn't even get to see Bayes theorem. So this right here is our Bayes theorem right here, a Bayes equation, sometimes called too. And it's not really that exciting. Like, I don't know, maybe it looks exciting to you guys, but we've actually seen this before too, like when we talk about probability. And so we notice that what this represents, like, oh, the probability of A such that B happens is equal to the probability of B such that A happened times the probability of A divided by the probability of B. And remember, A and B are events, right? Like, if this happens, then this would happen too. So for example, the event A could be the probability of landing heads, you know, based on this event. Okay, so there's different parts, and we usually call these different things. So like P of A right here, I can't really highlight that really well. P of A, that is called our prior. So this is kind of like what we believe, you know, our prior belief, right? And then our PA such that B, this guy right here, this is our posterior. So this is the thing that we will update our prior to be. So it's like, oh, we have our prior and we'll update it to our posterior, okay? And then you'll see this P, I can't really highlight this well, but P of A, B such that A divided by P of B. Sometimes we separate that out, and that's kind of like the likelihood. And likelihood is kind of like probability, but likelihood is kind of like saying the probability of our probabilities, if that makes sense. Like, what are the chances of our probability being correct, essentially? That's what this represents. So this is basically this equation. If you just have this equation and fill in the different parts, it's actually quite easy. I don't have this in the notebook because this actually happened relatively recently. You guys know 3 Blue 1 Brown on YouTube. I mentioned that person. They actually had a recent video, not too recent, it's like 2 or 3 months ago, about Bayes' theorem and stuff. And they actually do a great job visually showing that. So maybe if we have time, I'll kind of show you guys visually how you can build this up. You can also do a similar thing, which I've seen before, which is like using a chart essentially of like saying, well, if this happens and this happens. But the idea here is that there's a condition that we can know, like the real reason why people talk about this, like, well, okay, like this is like just how you manipulate the equation, right? You guys can derive this if you wanted to based on what we learned earlier in the module. But the real reason why this is super strong is that usually it's a lot easier to find out some of these things than trying to measure this directly. And so you can actually use this information here to help us help you update into a posterior and get a better view of what the chances are, okay? And so I'm going to give a quick example of that in a second. But before I move on, does anyone have any questions or any comments about what we talked about so far with this math equation?